Hello, this begins our coverage of topics in Chapter 6. Recall that register indirect addressing is indicated by brackets around a working register, and that the contents of the working register are used as the effective address of the operand. The PIC 24 supports these other forms of register indirect addressing. This form right here is called register indirect with pre-increment, indicated by having a double plus sign before the working register name. The way that this works is that the register will be incremented before the value in it is used as the effective address of the operand. In a byte mode operation, it's incremented by 1. For a word operation, it's incremented by 2. Register indirect with pre-decrement will decrement the value in the working register before using it as the effective address of the operand. For byte, it will decrement it by 1. For word, by 2. It's indicated by having a double minus sign in front of the working register of name. Register indirect with post increment, indicated by the double plus sign after the working register, will use the value in the working register as the effective address and then increment the value in the working register. Register indirect with post decrement has a double minus sign after the working register name. Again, it will use the value in the working register as the effective address of the operand and then decrement the working register value. Finally, register indirect with a register offset has an additional working register specified between the brackets that is added to the first working register value. The effective address of the operand is going to be the sum of these two register values. Notice that this works the same for both byte mode operation and word operation, and that WN and WB registers are unmodified. Let's look at some numerical examples to better understand how these new indirect addressing modes work. The first example we'll look at will be a move where the source operand uses register indirect with pre-increment using register W0 to register W2 using register direct addressing. The first thing we're going to do is we're going to determine the effective address of the source operand. Pre-increment says to increment the contents of register W0 before it is used as the effective address. So the contents of W0 is going to be 802. We're going to increment this register contents by 2 because this is a word operation. The new value of W0 will be 804. That's going to become the effective address of the operand. This 804 is going to become the new value of W0 after this instruction is finished execution. We're now going to take the contents of 804, which is C7A6, and we're going to copy that to our destination register with this our operand, which is W2. So the new value of W2 is going to be C7A6. Note that this instruction is modifying two registers. It's modifying W0 because of the pre-increment register indirect addressing mode, and W2 as a result of the move operation. This example is going to say move the source operand using the addressing mode of register indirect with post increment to the destination operand, which is register direct W2. The first thing to do is to determine the effective address of this operand. That's going to be the contents of W0 or 802. We're not going to increment W0 until after we have used the contents of W0 as the effective address of the source operand. So we're going to take W0, which is 802, and we're going to look at the contents of 802, which is going to be 4E81, and that is going to be the value that is going to be moved to the destination, W2. After that is done, we're now going to do the post increment operation. We're going to take the value of W0 and add 2 to it. That's because this is a word operation, and that's going to be the final result that's going to be stored in W0. As of this operation, two registers are modified. W0 by this post increment addressing mode, and W2 because as a result of the move operation. Notice that in both with this instruction and this instruction, W0 ended up with the same value, 804. However, W2 ended up with different values, because in this example, W0 was incremented before the move operation was done. In this case right here, W0 is incremented after the move operation is done, causing W2 in both cases to use different effective addresses for the source operand. In this case, the effective address for the source operand was 804. In this case, the effective address of the source operand was 802. This instruction is going to be a move.byte register indirect with pre-decrement to the register W2. Let's first determine the effective address of our operand. This is pre-decrement, so we're going to decrement the contents of W0 before using it as the effective address of the source operand. Because this is a byte operation, we're going to decrement by 1, so the effective address of our source operand is 801. So let's look at the contents of 801. The contents of 801 is going to be the most significant byte of this word address 800, which is going to be 90. That's going to be moved to the least significant byte of W2. So after execution, our new values will be W2 will have the new value of FB90, only its least significant byte is affected. W0 will have the new value of 801. This example here says move.byte register indirect with post decrement using register W0 to a destination of W2 using register direct. First thing we'll need to do is determine the effective address of our source operand. That's going to be the contents of W0, which is 802. So we'll use that as the effective address of our source operand. So we'll grab the contents of 802, which is going to be the least significant byte of this word 802. So the value 801 is going to moved into the least significant byte of W2. So our final value of W2 is going to be FB81. Then we need to do the post decrement operation. Because this is a byte operation, we'll decrement by 1. So W0 will get the new value of 802 minus 1, or 801. At this point, these two registers have been modified. W0 by the register indirect with post decrement operation, and W2 by the effect of the move operation. This slide shows a couple of examples of register indirect with register offset addressing modes. Here we're going to do a move where the source operand is using register indirect with register offset, where we're taking W0 and adding it to W1 to form the effective address of our source operand. So W0 has an 802, W1 has a 2. So if we sum those together, we'll get an effective address of 804. So we'll take the contents of 804, which happens to be a C7A6, and move that to W2. Note that neither of these registers, W0 and W1, are modified. The only register that's modified is its destination register, W2. This example is the same as this example, except this is going to be a byte operation, whereas this is a word operation. So the effective address is computed the same way. Take the contents of W0, which is 802, add it to the contents of W1, which is going to be 2, from the effective address of 804. So grab the byte stored at 804, which is going to be this least significant byte here of 804, A6, and copy that to the least significant byte of W2. So our final value of W2 will be an FB A6. Notice that this effective address calculation here was not affected by the .byte operation. This effective address calculation is the same it was done for this word operation. We're going to find that the previously discussed register indirect addressing mode is going to be useful for whenever we write PIC24 code that implements C code that uses pointers or arrays. We're first going to begin discussion of C pointers and how they work. In this C code over here, the first line here is going to declare two 16-bit unsigned variables, K and J. K is going to live at location 800, and this C line here is going to assign it the value 8245. J is going to live at location 802, and this C assignment here is going to assign it the value 9FC1. This next statement here is going to declare a pointer variable that is a pointer to an unsigned 16-bit uint data type. We declare a pointer variable by having a type name followed by an asterisk. We're going to use a P in the variable name to indicate that this is a pointer variable. The next question is, how big is a pointer variable? Is it 8 bits? Is it 16 bits? Is it 32 bits? How large is it? It turns out that the size of a pointer variable is dependent upon the particular C compiler. The C compiler for the PIC24 uses 16-bit pointer variables. Why does it use 16-bit pointer variables? Because pointer variables for the PIC24 compiler are pointing to data RAM, and the maximum size of data RAM on the PIC24 is going to be 64 KI addressable locations. This means that it has 2 to the 16th memory locations. So a pointer needs to be 16 bits in order to contain an address into this data RAM. So it turns out that it does not matter what a pointer points to. It could point to an 8-bit value, it could point to a 16-bit value, it could point to a 32-bit value, but all pointers on PIC24 that point to data RAM are going to be 16 bits wide. So we're going to assign this pointer variable to the next word in memory, which is going to be 804, and we're going to leave its value uninitialized at this point. So our pointer is going to contain the address of some other variable. How do we initialize a pointer? This line right here shows pointer A being initialized to the address of J. The ampersand operator is called the address of operator, and this is what we use to get the address of a variable. Once we make this assignment, if we look at the value of A, it's going to have in it 802, which is the address of J. So if a pointer is pointing at a variable, how do we get the value of what the pointer is pointing at? This line shows that. Here we have K is equal to what the pointer A is pointing at. Here we're using the asterisk operator. That's going to be called the dereferencing operator. What that's going to do is going to say, all right, go get the value of this pointer, which in this case is going to be 802. We're going to go to what that's pointing to, which is location 802, and we're going to get a 16-bit unsigned variable from that location, since this is a pointer to a 16-bit variable. So we're going to return the value 9FC1, and that's going to be copied into K. So after 4 is executed, K value is going to equal to 9FC1. If you're trying to relate this to PIC24 semi-language, you can treat this dereferencing operator here as if we had brackets around this pointer, which is saying we're treating this as an indirect address. So we're going to go through this pointer, go to there, get that address 802, and return the data type of whatever we're pointing at. Here we're pointing at, we said it was a pointer to an unsigned 16-bit variable, so we return the 16-bit variable. If this was a pointer to an 8-bit variable, it would return an 8-bit value. If it was a pointer to a 32-bit value, it would return a 32-bit value. Note that we really do not need these numerical memory locations to understand how the C code works. Here we said that pointer A is equal to the address of J. So when this says get the value of what A is pointing at, since it's pointing at J, we're going to copy the value 9FC1 into K, which is the current value of J. So we don't have to actually know these memory addresses here to know how this code works. This was simply provided for illustration purposes. Let's now change the previous example such that K and J are going to be unsigned 32-bit variables, and A is going to be a pointer to an unsigned 32-bit data type. The end result of the C code is the same. K and J are assigned values. The pointer A is assigned to the address of J, and then what A is pointing at is copied to K. Since A is pointing to J, then the value that K ends up with is going to be the value of J, which is this constant value. The main thing to note on this side is that K is now going to take up 2 words of memory, or 4 bytes, because it's now an unsigned 32-bit value. Same with J. But the most important thing to note is that even though A is a pointer to an unsigned 32-bit value, it still is 16 bits. All pointers are the same size regardless of what data type that they point at. This is pointing at an unsigned 32-bit value, but in terms of its size, it's still 16-bit because it contains an address. An address is going to be a location in data RAM on the PIC-24. One more change that occurs on this side is that the address of J has changed from the previous slide. The address of J, the starting address of J is now 804. That means that when this statement right here, 3 is assigned, where I'm saying assign to the pointer A the address of J, then the value that gets copied into the pointer A location is going to be 804 because that's the starting address of J, which contains the least significant word of J. So please remember, pointer size is always 16 bits and is not dependent upon the reference data size. It doesn't matter what type it points at. It could point at 8-bit data, 16-bit data, 32-bit data. Pointer size is always going to be 16 bits because it contains an address that's going to point to data RAM. Now let's see how we'd implement these C statements in PIC-24 assembly language. We're going to reserve space both K and J. Since they're 16-bit variables, we'll assign 2 bytes for each, or 1 word. When we're implementing a pointer, in our examples, what we're going to do is we're typically simply going to use a working register to represent that pointer and then use indirect addressing to implement the pointer operation. So in this case, the pointer A is not going to be assigned any space out here, but instead we're simply going to use register W1 to implement this operation. So first of all, we're going to move the immediate value A25 into W0, then move that into K. We'll do the same thing for J. We'll move the immediate value 9FC1 to W0, then move that into J. At this point, we want to assign the address of J to A. So we're going to do that in this way. We're going to say move immediate U16J to W1. What does this do exactly? Recall that U16J is a label, and that's representing an address. So this is saying move the value of the label, which is the address of J, into W1. At this point, W1 will have the address of J. If K starts at location 800, then J will have the address 802. So this is essentially saying move the immediate value 802 into W1. Then at this point we'll say move the contents of what A is pointing at to K. So we're going to do that via an indirect addressing mode, just a register indirect. This is essentially the same as saying move indirect through pointer A. Well, W1 has the address of J, so we're saying move register indirect W1 to W0, then move that to K. Now let's see how that PIC-24 code changes when we change K and J to be 32 bits wide and we change A to point to an unsigned 32-bit variable. We're not going to show the code for this initialization. It's straightforward. K is going to be assigned a space of 4 bytes or 2 words. J will be assigned a space of 4 bytes or 2 words as well. We're still going to use W1 for this pointer. This statement right here, in which we assign pointer A to the address of J, is going to be implemented in the exact same way as before. We'll remove the immediate value of the U32J label into W1. If you're keeping track, and if K starts at 800, then J is going to start at 804, which means that this 804 is going to get loaded into W1, and now W1 has the address of J. Now let's implement the C statement, which says take the contents of what A is pointing to and copy it to the variable K. We have 4 different implementations that we're going to discuss simply to show you the flexibility of the PIC-24 instruction set. This first implementation here is going to make use of the move.doubleword instruction. Recall that the move.doubleword instruction allows us to copy 32-bit values around. Our approach is going to be to use the register pair W3, W2 as a temporary holding register. And what we're going to do is we're first going to copy what A is pointing at, the 32-bit value A is pointing at, to this register pair. Then we're going to copy that register pair to the K memory location. So let's get started. We're going to do move.doubleword register indirect W1 to W2. Recall that W1 has the address of J. This is going to copy the least significant word of J into W2 and the most significant word of J into W3. At this point, we now need to copy W3, W2 to K. The way that we'll do that is we'll move the address of K into W1. Now we can use the reverse move. We can say move dot double word the register pair W3, W2 to the memory location pointed to by W1, which is going to be K. At this point, these three instructions have copied what A is pointing at to K. This next implementation will simply use word move instructions to implement this assignment operation. So let's get started. We're first going to say move what W1 is pointing at, and recall that W1 is pointing at J. Move that word to W0. So it's going to move the least significant word of J to W0. We then get to copy W0 to the least significant word of K. At this point, we now need to do the most significant word move. However, W1 is pointing at the least significant word of J. To get it to point at the most significant word of J, we need to increment W1 by 2. At this point, we can now repeat this move, except this move is now going to be copying the most significant word of J to W0 and then writing that to K. This implementation will be the same as this implementation approach, except we're going to remove the need for this increment 2 by using the register indirect with post increment addressing mode here. This is still going to move the least significant word of J to W0, but after that move is done, it's going to increment W1 by 2. Recall that the post increment addressing mode will increment by 2 if this is a word operation. At that point, W0 has the least significant word of J, so then we'll move W0 to K, least significant word. Then we'll, since W1 is now, by the fact that this post increment is now pointing at the most significant word of J, we can now copy that in W0 and then move W0 into the most significant word of K. This approach is going to use W2 to contain the address of K. At that point, we can say move what W1 is pointing at, and W1 is pointing at the least significant word of J, to what W2 is pointing at, and W2 is pointing at the least significant word of K. Because we're using the post increment addressing modes, both W1 and W2 will then be incremented by 2, which means that they will be pointing at the most significant words of J and K. So now we can say move what W1 is pointing at to W2, which will move J most significant word to K. So, which of these approaches do you use? It's easy. Simply use the approach that you best understand. Let's finish off this introduction to C pointers by discussing pointer arithmetic. Pointer arithmetic means to add or subtract a pointer by some value. The value being added to the pointer or subtracted from the pointer is multiplied by the size in bytes of what the pointer is pointing at. Here we have three code fragments. They're similar to each other in that both declare a pointer and both declare two variables. The code itself is going to take the address of a variable, assign it to the pointer, and then increment the pointer by 1. They're different from each other in that this uses 8-bit variables, this uses 16-bit variables, and this uses 32-bit variables. Let's take a look at this pointer arithmetic where A is pointing to an 8-bit data type. Here we're incrementing by 1. What that actually means is that we're incrementing, taking that 1 and we're multiplying it by the size of in bytes the UN8 data type. The UN8 data type is 1 byte, so we're actually incrementing this by 1. What about for a 16-bit data type? Here we have A as a pointer to a 16-bit data type. We increment it by 1 in C code, what is actually going to happen is we're going to take that 1 and multiply it by the size of a UNT16 data type in bytes. A 16-bit data type is 2 bytes, so we're actually incrementing that pointer value by 2. Why is this happening? What's going on here? Well, let's assume that U16J was sitting at the memory location 802. And let's assume that K was sitting at memory location 804. When we have pointer A pointing at J, that means that pointer A is going to have the value 802. When we increment this pointer by 1. It's pointing to a 16-bit data type. We want it to point at the next 16-bit variable. Well, where's the next 16-bit variable? It's 2 byte locations away. It's sitting at 804. So we need to increment it by 2. Similarly, if we looked at this example up here, if we let's assume that J is sitting at 802, because a UNT data type is only 1 byte wide, that means the next variable, byte variable, would be sitting at location 3. So this would be J and this would be K. If we increment this pointer variable here, it's going to now point the next byte location, the next byte variable, which is going to be K, so we need to increment that by 1. For this 32-bit case, when we increment A by 1, we're saying 1 times the size of a UNT32 data type in bytes. 32-bit data type is 4 bytes, so we're actually incrementing it by 4. Using the same starting memory locations, if we assume that J is sitting at 802, then that means that K would be sitting 4 bytes away. It would be sitting at location 806. And so when we increment this by 1, we actually have to increment this pointer value of 802 by 4 bytes to point at the next 32-bit variable. Notice that the C code has all of these variables being incremented by 1. However, when you translate this to PIC24 code, it's your responsibility to actually increment this pointer value by the correct amount. In this case here, let's look at, first of all, this implementation. We're going to move the address of J into W1, so we'll use W1 for the pointer variable A. Now when we increment this pointer variable, since it's pointing to a UNT data type, which is 1 byte, we'll simply add 1 to that variable. So here we've added 1 to pointer A. This code would be the same as that in terms of loading the address of J to W1, but now in order to implement this, we actually have to increment this pointer value by 2 bytes as seen in the previous slide. Similarly, since in this code right here, A is pointing to a 32-bit data type, once we've loaded the address of J into W1, in order to increment this and implement it in PIC24 assembly, we actually need to add 4 to that pointer variable.